So at any one point in time, if you have questions, please let me know. Okay. Okay, I'll start. I hope y'all can hear me. Just begin. Okay. For question one, right? The question is actually on some basic application of Hess law. Okay, so I hope you don't find it too difficult. So basically, they discuss or they ask you some of the common questions which you expect. So for example, for question 1A, the key idea here you might want to take note of, right, is they ask you to reference to the type of structure and bonding. This is a very common way Cambridge asks questions, as well as school asks questions. So whenever you encounter questions related to chemical bonding, right, they ask you things like, with reference to structure and bonding, there is a need for you to indicate to us what kind of structure you expect for the compound in the question. So in this case, the question is asking you calcium fluoride. So before you even explain, right, you have to highlight to us that calcium fluoride is actually an ionic compound, and then discuss a little bit regarding its structure. Like the usual things you have in the notes, for example, giant ionic, etc. Okay. Of course, the main question here, the focus is on why is it brittle. Yeah, so there are two parts. One is the structure and bonding, the other one is brittle. Yeah, so if you look at some place in the notes, right, it was kind of written that like ionic compound is brittle, because if you apply some force, right, then maybe the plane will slide, and then once the plane slide, maybe light charges faces each other, which will cause electronic repulsion. Yeah, so I think a simple sentence like this will do. Okay, I'm just going to show you one of the sample script from one of your classmates, so that you have a better understanding. And in that case, it also helped me in my debrief. Okay, so for example, this particular classmate of yours wrote that the first point here, it was mentioned regarding the giant ionic compound. Okay, and then don't really need to talk about this portion. Yeah, so this portion, whenever we try to answer questions, right, we will want to be as concise as possible. So maybe I should say avoid spamming. Okay, avoid spamming. Of course, you are still learning now. So I mean, it's fine, you learn along the way, but avoid spamming, because if you spam, sometimes you spam too much, then you don't have enough time for the questions at the back. Yeah, so you don't need to keep writing and writing and writing. Yeah, so I think the main thing is focus on what the question asks you. Okay, and then of course I do understand from the perspective of the student, because from here you say a lot of energy is required, and then after that you talk about therefore your calcium fluoride is hard and rigid. Maybe there's some relation, yeah, but that's fine. If it's a style of your writing, we'll just leave it. Okay. So when a very strong force is applied, it will force ions of like charges to be displaced next to each other, so that it will cause electronic repulsion. So that's fine. Yeah. Okay. So I think 3 or 4 liners like this will do, and you will get your 2 marks. Okay. Yep. The next, I mean, if there's nothing, I will just move on. The next part is on Born-Haber cycle. So there are 2 things I want to focus on. Maybe I will also incorporate a little bit of revision as well. For Born-Haber cycle, right, I want you all to remember how you learn it in our tutorials and of course lectures. It must be drawn in the form of an energy level diagram. This is very, very important. Okay, so let me repeat. Your Born-Haber cycle, right, must be drawn in the form of an energy level diagram. If you're asking me why, it's a bit difficult for me to tell you why at least at the H2 level. Because actually at the H2 level, there seems to be some form of a requirement and understanding that whenever we ask the students to draw bond-Hebel cycle, although there's a word cycle there, right? The student need to display, okay, in the form of an energy level diagram. Of course, you know how to draw an energy level diagram, so it will look something like this. Okay, and some of the important thing I thought I want to highlight to you, right, includes things like you need to label your axis. In this case, there's only a vertical axis. Yeah, so the vertical axis is in terms of energy, kilojoules per mole. Make sure you put in your units. Okay, if not, the rest of our numbers don't make sense. And then the next thing is you need to have your zero. You need to indicate to us, right, at the elemental level, where is that energy? So the reference point is of course zero lah. So in that case, I'm looking at calcium and fluorine. Okay, and then the rest you can just leave it. Yeah, but just make sure that you write them in the correct order. So of course, the most common mistake that students will make is the students will forget to include the electrons. So we'll look out for this because we know that students will forget. Okay, so we'll look out for it. And then of course, you're supposed to find electron affinity. So make sure you indicate it in your von-Hebel cycle. You can either spell it out or write in short forms, or you can say you let it be X. So in this case, it will be 2X. Yeah, so that is easier for you. Okay, so once you have everything, make sure you sum everything up correctly. Yeah. Some of you still have problems doing the summation, and then you get a lot of problems showing the wrong direction of the arrow, and then somehow you combine your steps as well. So make sure that you don't combine your steps. Okay, so these are all individual terms. So for example, this is minus 1220 is actually the enthalpy change of formation. Okay, and then the first one is actually atomization enthalpy. The second one, 177, is actually atomization enthalpy as well of calcium. So make sure you separate them. Of course, if you recall what I said to you in the tutorials, for similar terms, you can combine them. So no problem. You can add 158 and 177 together. So you can atomize both together. Okay, and ionization energy, you can combine them as well. No problem. Okay, but for electron affinity, right, don't combine with IE because we want to ensure that you understood you have to ionize first before you gain electrons. Yeah, so these are the little things you need to take note of. If not, precious credit will just be deducted away. Okay, I didn't give you I didn't give you any marks, but I think from your from the crosses you get, or from the carrots you get, you roughly know like what is missing from your part after I debrief you. Okay, then make sure you sum them up properly. So in this case, when you sum them up, again, just do it properly. I mean, there's no better way to tell you this except to look at what you are familiar with. So in this case, for this for your classmates, what he or she is familiar with is he or she prefer to look at everything downwards. If you realize, you see, everything is downwards. So electron affinity minus 2613 equals everything downwards as well. So anything that is pointing up, right, he or she will just swap the sign. Okay, so you notice all this is quite obvious. Yeah. So just make sure you have a way to do all this summation and you are comfortable with it. And then whatever ways you want, you can stick to it, and then and then that's it. I mean, you will never forget it. You will never forget it because there's nothing to memorize here. Yeah, remember this. There's nothing to memorize. It's just factors. Okay. So some students prefer to just do it one shot. For example, maybe you prefer to look at it from electron affinity perspective, and then if you prefer to look at it from electron affinity perspective, then when you sum them up, you will have to go this way, down and then up. Okay, so when you sum down and up, right, then whatever arrow that is pointing up, you have to swap the sign. Okay, and then whatever arrow that is in the same direction, then you just leave it. Okay, so it's really finding your own voice and how you want to go about solving it. So there's no hard and fast rule. Okay, yeah, so you should get minus 341. So when you punch your calculator, make sure you punch it correctly. Some of you, I think, punch it wrongly, and then you get all sorts of different answers. I also don't know how you end up with those answers. Okay, I hope there's no issues. I'll move on. I mean, if you want to voice out, you just unmute yourself and then let me know. Okay. For 1B2, I think 1B2, the question is a very standard question. I think you have it in your lecture. I mean, in our consolidation test as well, right? The numerical value of lattice energy of magnesium fluoride versus calcium fluoride. Yeah. But again, in terms of answering, right, I think as I mentioned in the debrief to your consolidation test, there is a need for you to state this particular relationship either in words, or in an equation format. And remember that the relationship is a relationship, it's not an equation. So lattice energy is directly proportional to the product of the charges, inversely proportional to the sum of the ionic radii. Yeah, so I think you have to be aware of that. One common mistake, or rather one common mistake in terms of writing, maybe you can call it being sloppy in the way you write or what. Because you realize that actually both your ionic compounds is fluoride, right? So some of you tend to say that, oh, in that case, right, lattice energy is directly proportional to 1 over R plus. Yeah. Just take note that when you write it this way, right, it's actually not correct. Yeah, it's actually not correct. This is not correct. Because the denominator is a summation. Yeah, so you cannot just say, oh, because the NIO is a common between the two, right? So therefore, lattice energy is simply inversely proportional 1 over plus. It's not correct. Okay, so when you write it out, right, you still have to indicate it as because both have the same charges. So lattice energy is thus dependent on the sum of the ionic radii. Yeah, something like that. And then you say that, oh, because Mg2 plus is smaller than calcium 2 plus, therefore I expect the numerical magnitude of lattice energy for magnesium fluoride to be larger. Or you can say it has a more exothermic lattice energy. Really depends on what the question is asking you. The question is asking you numerical magnitude. So in this case, you don't say more exo, you just directly say that the numerical magnitude is larger. Yeah. Okay. 1C is the one with quite a bit of issue, because most of you just give a, I won't say standard response. You tend to give whatever you thought is convenient. Although I can't really blame you in that sense. Yeah. Okay. So you are given two compounds X and Y, right? You were told that X has a higher boiling point. Yeah. So keyword here is boiling point. Yeah. Keyword is boiling point. So we're talking about boiling. So from liquid to gaseous phase. Now, most importantly, right, you have to look at the dipoles, which is quite crucial here. So my fluorine is delta minus, right? Then, of course, my N is delta plus. Okay, so there's a dipole going in this direction. There's a dipole going in this direction. And then for Y will be in this direction, and the other side will be in opposite direction. You realize that for compound Y, right, the dipoles cancel. So essentially, this leaves Y to be a non-polar compound. For X, it doesn't cancel. So there's a net dipole going downwards for X. So in that case, when you draft your answer, right, you have to focus on the fact that the intermolecular forces of attraction between molecules of X, right, is permanent dipole interaction. Yeah. So remember, you have 3 marks here. Okay, so that means that when you draft your answer, right, your answer has to be quite substantial. Okay, meaning that you have to go step by step to explain to us why X has a higher boiling point. Yeah, so the step-by-step part, I think I demonstrated briefly to you earlier on. I think the first thing you need to do is to showcase the fact that X is polar, whereas Y is non-polar. Okay, and of course, there is a need to indicate to us how are you aware of that. Okay, then after that, identify the correct intermolecular force of attraction. Yeah, so X is PD, Y is dispersion forces, because it is, because there's no dipole moment, right? There's no net dipoles, so therefore dispersion forces will be the main intermolecular force of attraction. Okay, then once you identify that, then you have to finish off your question by highlighting that I need more energy to overcome the stronger PD between molecules of X as compared to that in Y. Okay, so very, very important. You need to recognize that. Okay, yeah, so that's how you get your 3 marks. So from understanding which one has a net dipole, which is polar in that sense, to identifying the correct intermolecular forces of attraction, to telling us you need more energy to overcome the one with the stronger intermolecular force of attraction. Okay, and then conclude which one has a higher boiling point. Yeah. Okay, any questions? Okay, the next part I'm going to discuss will be part D. Okay, so for part D, right? Yeah, part D is an interesting question in that sense, because okay, so for part D, right, I sort of realized that a lot of you, or rather most of you, right, have this little bit about chemical bonding, especially covalent bonding, that is kind of lacking. Again, can't really blame you, because it could be the fact that you are not kind of exposed to that in the course of the study of chemical bonding, but that's fine. I mean, once you're exposed to it, then I think you'll be more aware how to go about answering questions. Okay, so I need to tell you a little bit about the motivation of this question, the reason why behind the question. If you look at the question, right, they are actually sort of telling you that, okay, when I have hydrogen and phosphorus having very similar electronegativity values, so one is 2.1, the other is 2.2, right? You realize that when we look at the bond energy, for hydrogen is 436. Phosphorus is 208. Then for phosphorus hydrogen, right, it's kind of like in between. It's kind of like an average, although it's not exactly an average. I think this can be quite easily understood. I'm not sure whether you are confident of saying that it can be quite easily understood. Because for HH, right, essentially we're looking at the overlap between the 1s valence subshell and the 1s valence subshell of each hydrogen. For PP, right, we are probably looking at between 3p and 3p. Okay. Of course, you have to bear in mind that we're not going into hybridization because we don't want to complicate matters. Yeah. Anyway, it doesn't really matter because we are looking at period 3 subshells. So whether you're talking about 3s or 3p, I don't think it matters so much, but it's more of 3p if you are simply isolating it out. And then for P and H, we are looking at 3p and 1s. Okay. Now, the larger your valence subshell is, right, that actually means that the overlap is not as effective because now, for the same number of electrons, it is more spread out in the larger orbital. So in that case, you expect the overlap to be poorer. And if the overlap is poorer, the bond will be weaker because on the average, the electron pair will spend its time at around the period 3 subshell region. Of course, when they form a bond, you don't really call it a period 3 subshell region, but you get the idea. So on the average, it will be further away from nucleus as compared to a 1s overlap. So I think this can be easily understood when we are looking at 1s versus 3p. Okay, then for a simple logic between a 3p and 1s, then therefore we expect somewhere in between because I'm using period 1 and then I'm using period 3 valence shell to overlap. So therefore I expect the electron pair to to meet halfway between the two. So I think the average value here, you can easily come to terms with it. It's not something that is a rocket science. Yeah. I mean, simply by looking at size, I mean, simply like looking at proportions, okay, by the relative size, I think you can understand it. Uh, However, it's not always the case because you have to bear in mind that electronegativity value does play a part. But in this case, for H and phosphorus, it's about the same value. Yeah. But in the case of fluorine, right, it becomes a bit interesting because for fluorine, the electronegativity value is actually 4.0, which is way bigger than the other two. Now, when it's 4.0, right, what do you notice about the bond energy? You realize that now the FF bond, right, is weaker than PP bond. Of course, for this question, we're not going to explain why FF is weaker than PP. That's not the scope of the question. But most interestingly, right, your HF bond, right, is like even stronger than a HH bond. So now they ask you the reason why. Yeah, so that's the purpose of this question. So they're asking you the reason why. And of course, how do you go about answering it? Okay, I think the first thing you need to recognize, right, is that you have to kind of like tell us that my pH bond, right, is not a polar bond, or is largely non-polar as compared to HF, which is a polar bond, which I think you can tell because of the electronegativity difference. So I think first thing you need to mention is the polarity of the pH bond versus the HF bond. So recognizing that they are polar already earn you 1 credit. So that's quite kind of straightforward. And then the next thing you need to follow, all right, is by explaining to us why is a polar bond stronger than a non-polar bond. Yeah. So that is something that that is missing in quite a lot of the answers, even if you manage to hit the polarity part. Okay, you will notice from your data booklet, right? Actually, simply by just going through your data booklet, you'll realize that a non-polar bond like CC, right, is always weaker than a polar bond like CO. Okay, like a C double bond C is always weaker than a C double bond O. Yeah, then a C single bond N is always weaker than a C. Also, sorry, a C single bond C is always weaker than a C single bond N. Yeah, so the polar bond is always stronger. Why is that the case? Yeah, then you have to recognize the continuum of bonding, right, between a perfect ionic and a perfect covalent bond. Okay, so that actually means that when you have a polar covalent bond, it has what we call an ionic character. Yeah, so when we look at HF, right, it's not simply HF, but HF has a delta plus at one end and a delta minus at the other end. Yeah, so this partial ionic character, right, actually strengthen the bond because in the interior, right, it has not only does it have the electrostatic force of attraction between the nucleus of H and F with the bonding electron pair, but at the same time, right, this strengthening is due to the ionic character between H and F. Yeah, this so on the whole, this actually leads to the strengthening of the HF bond, which has to be mentioned in your answer because a lot of you simply just say, oh, they are polar, so therefore it's stronger. But you have to move in and say that, you know, the partial ionic character strengthen the HF bond. Yeah, of course, the if you want to go deeper, then it's not within the scope of the syllabus, but the deeper explanation, of course, yes, you have to have a appreciation of molecular orbital theory, yeah, which actually tells you that a polar bond, right, the bonding electron pair actually is deeper in, and it has a stronger bonding character. Yeah, in terms of molecular orbital, but we won't go into that now. Okay, if you're interested, you can always Google it and then you see some information. But of course, if you read them, you might be a bit lost because some of the information are written in a relatively convoluted manner. But nonetheless, it gives you some idea. Yeah. Okay. Any questions? If not, I'll move on to E. Yeah, E is simply a drawing question. Again, I have no issue with this for most of your answers. The only thing I have, okay, I won't say the only thing I have. The issue I have is, of course, largely on some of the missing things. Answer. I think the first thing is you have to label. So some of you didn't label. You must put hydrogen bonding, and then if it's ion dipole, you have to put ion dipole. Okay, and then make sure that you have your delta plus, delta minus, delta plus, delta minus around. Okay, and when you show the intermolecular forces of attraction, right? Please do not lock them up in a square. Yeah, because you know from thermodynamics that it is entropically not favored. So don't do that. Okay, just show them up as H. The F indicate hydrogen bond with the H in ethanol. That will be okay. And then make sure you have your lone pair as well. Okay. Yeah, so these are the little things. Yeah, same as ion dipole interaction. So you have your delta minus delta plus, you have your lone pair, and then your sodium is a positive charge. So it doesn't have delta plus. So it's a positive. Just one pair will do. Okay, just like that will do. Don't need to draw too many. Okay, so just like that will do. And then for the case of fluoride, make sure you have your lone pair as well on F, and then your dipoles. Okay, just very simple thing lah. I mean, all this nobody will tell you again next year because you would be expected to be able to produce them. Yeah, and you will be asked one way or another lah. So I think it's good to learn them well. Okay. Yeah. Any questions for one? No? If not, then I will move on. Okay. Okay, for question 2, right? Let me see what question 2 is. It's actually on. It's a pretty interesting question on the. They give you the IEs. Okay. This was the block test which I'm involved in 8 years ago. Was it 8 years ago? 2012 lah. So 9 years ago. Actually, time flies. Yeah. So I kind of like forget whether the values are exact replica from your data booklet. My understanding is not lah. It's like purposely taken from another place so that the values are very different. But correct me if I'm wrong lah. Okay, I may be wrong. Okay, so you have oxygen and an unknown A lah. Yeah, and then you were told that the atomic number is less than 20. Okay, so if you look at the trend, right, you will notice that for oxygen, right, 6 to 7. Okay. For oxygen, it's obvious. I don't think for oxygen, I need to explain to you lah. Yeah, because in that case for oxygen, right, between the 6th and the 7th IE, right, there's a huge jump. And this huge jump obviously is due to the fact that the 7th electron is being removed from the inner quantum shell. Okay, so with this same idea, right, you realize that for element A, right, the 7th to the 8th one is actually a huge jump. That's about a 20,000 jump. Okay, yeah, so that's something that you need to recognize. And then for 2A1, you are asked to write an equation for the IE which has a value of 3390. So this is for oxygen. Okay, very clear that it's for oxygen. So again, I think I mentioned to you all quite often, and especially the consolidation exercise, some of you made the mistake, right? When you write your IE, right, you must have the state symbols. Okay, and then after that, you are getting a doubly positive charge atom. I mean not atom, ion, and then electrons. Okay, the state symbols is important. Just make sure that you have them in your answer. Yep. Okay. Enthalpy change again. This is kind of like a repeat from question 1 because we want you to draw cycles again. Yeah. Then for those of you who can actually look at things relatively quickly, okay, I mean relatively quickly lah, you realize that it's actually the second IE minus the first IE lah. How do you manage to look at it relatively quickly? Well, I mean, if you look at the second IE, okay, if you look at the first IE, right, it's actually is O gaseous, you get O plus gaseous plus electrons. Yeah, so this is the first IE, and this is the second IE. You can look at it simply by swapping, inverting the equation. So it's like minus first IE. Yeah, and then in this case, these two will cancel off. So you get 2O plus here, and then O, and then O2 plus. Yeah, so it's like second IE versus first IE. Yeah, but when you are able to say it, right, could you also kindly respond it by writing a statement, or at least write a delta H equals to 3390 minus 1310, yeah, equals to 2080. Yeah, please write it out loud, because if not, then we don't know what you are calculating. Okay. Okay. Question A3 is probably the one that. Okay. Not A3, A4. Okay. So for A3, why is it group 7? Most of you get it correct. You mentioned about the inner quantum shelf for the 8th electron being removed. That's fine. But A4 is the one that a lot of you wrote quite interesting answers. Yeah, some of them quite complicated. Yeah, actually don't need to write in such a complicated manner, to be honest. Okay, the first thing I thought I just want to bring to your attention, right, is that for your element A, okay, not element A, yeah, okay, element A, you only have two choices. One is fluorine and one is chlorine, just two choices. Okay, so the question is asking you, why is it chlorine, not fluorine? So they will tell you that it's chlorine. It's confirmed chlorine, not fluorine. Then the first thing you want to recognize, right, is that what if it is fluorine? You get my idea. I think once you can explain to me why is it not fluorine, then I think it's easier. So to explain why is it not fluorine, I think you just look at the first idea. Here. Okay. So ask yourself, if it's fluorine, will the first IE be greater? It will be greater, right? Because if you look at the periodic table, right, oxygen, before oxygen is nitrogen, after oxygen is fluorine, and then after fluorine is neon. Okay, PCNOS, right? After fluorine is neon. Then what's happening is that in general, right, the first IE increases across the period. Of course, there are some dips, but then we're talking about in general, increases across the period. So if A is fluorine, right, the first IE will be greater, but in this case, it's smaller. Yeah, so you can simply use this argument to say that, oh, because the first IE of A is smaller than oxygen, therefore it is not fluorine. Yeah, it as simple as this. Because some of you actually went quite deep into the explanation. You went on to look at all the IEs. When you went to tell me, oh, the first, second, third, fourth, fifth, sixth, everything is smaller. But sometimes when you bring in too many ideas, then I also don't know what you're trying to say, because you say all is smaller, so therefore it is not fluorine. Yeah. When you bring everything in, it can be quite convoluted, because there is no focus in the answer. Yeah, so that's why some of you I wrote there, is there a simpler way to explain your case? Yeah. Or you can look at it from another angle as well. You can look at it from the perspective that, okay, because the first IE of A is smaller. Yeah, so therefore, it's probably chlorine because it has a larger, or rather it has one extra principal quantum shell. Yeah, but of course that answer is not as good, but of course I do give credit for that. Yeah, so actually the easiest answer is really just to tell me that no, A cannot be fluorine because the first IE is smaller. Yeah, I think a simple answer like this will do the trick. Yeah, you shouldn't be referring to data booklet for this question, by the way. Yeah. Okay. Any question? Okay. If not, I will move on to the next part, which is B. Okay. One thing about B is, I need to mention to all of you, right, regarding the drafting of your answers. Now, you need to be aware that your shielding gases, right, okay, is actually a mixture of argon and another gas. So when you answer the question, right, you cannot tell me, let's say if the answer is E, right? Let's say the answer is shooting gas E, right? You cannot tell me CO2, because it doesn't make sense at all. Yeah. So when you answer the question, make sure you use all the symbols, B, C, D, E. Don't just tell me CO2, hydrogen, helium, oxygen. It doesn't make sense. Yeah. So you have to be careful how you answer the question. Okay, so that's something I thought I want to make mention because I noticed that in your answer. Okay. B part one, I don't think is a major issue because it's so common that I think a lot of you are very familiar with really because we have it in our lecture test as well. Okay, so it can be, you can write it in a complicated way or simple way. It's really up to you. Yeah, as long as you can get your answer. Okay. Yep. I'll move on to part two. Okay, so for part two, right, you were told that the shielding gas mixture has a density of this, and then you're supposed to calculate, take note of what you're supposed to do, the apparent molar mass of the mixture. So in your answer, you have to tell me that this is actually an apparent molar mass. So a lot of you have this. Okay. And then the answer has to be in grams per mole because it is molar mass. Yeah. Okay, so just take note of it. It has to be grams per mole. Now, what is missing in a lot of your answer, I have to tell you, is that you did not write the deduction for me. You did not write the deduction. You simply just tell me is E or otherwise just any random answer. Now you have to deduce. You deduce means explain how you get your answer. So you cannot just tell me is D or E. Yeah. Okay. So once you calculated it to be, if I round up 41.0 grams per mole, right? How do you deduce that the answer is actually E? Okay, actually the answer is not very difficult. All you have to tell me is that because my shielding gas is a mixture of argon plus something, right? If argon's AR is 39.9 and my average is 41.0, the other gas MAR, right, must be greater than 39.9, right? And the only gas amongst this category that's greater than 39.9 is CO2. So therefore the mixture is E. That's about it. Just a simple response will do. Okay, yeah, but you have to deduce. You cannot just say, oh, it's E. Yeah, so the deduction part is missing in a lot of your answer. Yeah. Okay. Then for part three, you're supposed to calculate the amount of argon in 1 mole of the shielding gas mixture. But this part is interesting because a lot of you started to calculate for me percentage. They're asking for the amounts, not percentage. They don't want percentage here. Okay, so when you calculate amounts, you simply again just let it be x lah. Okay, so you let one be x, and then after that, for the then the other one is 1 minus x. Also, you blah blah, you calculate, and then x will be 0.732 moles lah. Yeah, something like that. This will do. Nothing complicated. Okay. And then finally, suggest which one shows greater deviation from ideal gas behavior. Again, same thing. We're asking you for the shielding gas mixture. So you say E, but you cannot just say, oh, E, because E has the largest electron cloud. What in E has the largest electron cloud? You get my point? What in E? So it's the mixture of CO2 and argon. Of course, you don't really need to talk about argon. You can just say, oh, CO2 has the largest electron cloud, so therefore it shows the greatest deviation for ideal gas behavior. Then why is that the case? Because it is the most polarizable, so therefore forms the strongest dispersion forces. Yeah, that will do the trick. Okay. Any question so far? Today you have been quite silent. No, Okay, next. Stoichio. Yeah. So remember your mid-year, right? Your midterm, you didn't learn much topic. So do expect some Stoichio to come up. Although Stoichio usually we test it in practical exams. Yeah. So do expect some Stoichio. I think if you can handle a question like Part C, yeah, that'll be great. That's good enough. Okay, so for Part C you have 10. Group 4, and then okay, then they went on to explain to you quite a lot of stuff. It's a mixed oxide, etc. Right? Yeah. So I think the calculation for most of you is not a big issue. I think, at least yeah. So for 2-1, you simply just use the KMN04 data to calculate for me, and you get the number of moles of tin2 to be 6.75 times 10 to the power minus 4. And then moving on is the parts that some of you have issues. When you calculated for me the number of moles of tin2 in the second titration, right, most of you can get this. Yeah, you can get this part. Number of moles of tin2. Yeah. But when it comes to the ratio, right, that is the problem. Remember, the ratio you have to take the difference. So for G, right? For G, the number of moles of tin2 plus to the number of moles of tin4 plus, right? You have to take the difference. So in that case, it would be, you need to take this number, subtract off 6.75 times 10 to the power of minus 4. All right. So in this case, this number retains. Okay. But for the other case, right, it's 0.001015 minus 6.75 times 10 to the power minus 4. Okay. And then you should get a 2:1 ratio. Thereabouts. Okay. 2:1 ratio. Okay. So of course this will affect your answer. So your part 3, tin2 oxide and tin4 oxide, no issue. So most of you can get it. But of course, for the case of this, because of the carelessness above, then most of the time your part 4 will be wrong. Yeah. So there are 2 ways you can write your answer. You can either write it, okay, because you have it in a 2:1 ratio, right? So you can either write it as 2 SNO dot SNO2, which is the usual way you represent answers if you have a mixed valence species, or you can simply write it as SN3O4, something like that. Okay, so either way will do. Yeah. Is it the first time you have seen this? Actually, no, this is not the first time you have seen this. Remember one of the consolidation stoichio redox calculation I gave you? The formula was Fe3O4 as well. And this is actually a mixture of FeO and Fe2O3. Yeah, if you recall that question. Yeah. So this is not the first time you have seen a mixed valence oxide. Okay, so sometimes it can be given to you in the question setting. Okay. And then of course for part 5, you are asked, I can also convert, powder iron can also convert all the tin4 to tin2, and then in the process my iron is oxidized to iron 2. So will the second title value be affected? So of course the answer is yes, because my iron 2 can also be oxidized to iron 3. Yeah, that's about it. So therefore the title value will be higher than expected. Okay, so this will be the key point you need to mention. Larger than expected title value will be required. Okay, Yeah, that's the end of question 2. Any issues? Yeah, if not, we will move on. Okay, we'll move on to question 3. Yeah. So 9 years ago, I said question 3. So you can see that the style of the question requires the students to actually do quite a bit of thinking. Okay, I think you can see from the format. Okay, so okay, for the first portion, actually you are given some clue if you notice, right? So the useful information is the group 2 metals undergoes thermal decomposition, and then the higher the charge density of the group 2 carry the lower the decomposition temperature. So there's a newly found element, or not element, sorry, mineral known as somaba, and then you have an unknown composition, sodium carbonate, magnesium carbonate, barium carbonate. So 5 grams of somaba was thermally decomposed. Okay, this this kind of graph, right? For those of you who are interested, it's known as a TGA. It's called thermal gravimetric analysis. So it's done using a computer connected to a analyzer. Okay, so you just put a sample in, and then you increase the heat, and then after that, this thing will just decompose like this. Okay, so it is this value is deliberately not given to you. Okay, it's not given to you because if it's given to you, then we don't need to ask you to do any calculation already. You can just do everything on your own lah. Okay, so you notice that at the start you have all the 3, right? Then after that, one of the carbonate completely decomposed. Then after that, 2 of the carbonates completely decomposed lah. So you are left with 1. How do you know you are left with 1? Like, how do you know? Okay, actually you don't really know lah. Okay, but then the question went on to tell you that the residue consists of sodium carbonate, magnesium oxide, and barium oxide. They already tell you the answer already. Yeah. So therefore, you know that one of the carbonate is not decomposed. Okay. Then therefore, from this scenario, right, you know that between magnesium carbonate and barium carbonate, obviously magnesium carbonate will have the lower decomposition temperature lah. The reason, of course, straightforward, because magnesium 2 plus has a greater charge density as compared to barium 2 plus. Okay, so the focus is on the charge density. Okay, and another thing I thought I want to highlight to you is that when you answer the question, right, when you talk about the cat ion, please tell me is Mg2 plus. Yeah. Some of you like to say Mg has a lower charge density, which don't quite make sense lah. Okay, and when you balance the equation, right, I hope you have done the correct analysis and check the things out properly lah. Because I only have X amount of sodium carbonate, Y amount of magnesium carbonate, and Z amount of barium carbonate, right? Definitely because sodium carbonate did not get decomposed, right? Sodium carbonate is X, so I shouldn't have any X in my CO2. And then because I started with YMG, right? I only have YMGO here, so I started with ZBA, then ZBAO here, so it's quite, in that case, then the CO2 will be Y plus Z. Okay, so technically this balance equation should be quite easily obtained, but you just have to be a bit careful in the way you draft your answers. Okay, yeah, so that's how you go about doing that. Of course, now the calculation is the difficult part lah. I mean, I have to admit, the calculation is really the more difficult one. But I won't say it's difficult lah. It's just a bit. I mean, you just have to be very clear what you are calculating. Yeah. So you are told that the residue obtained from the complete thermal decomposition was fully dissolved in excess hydrochloric acid. The first thing you need to ask yourself is, will everything react with hydrochloric acid? Okay, because your residue is sodium carbonate, MgO, and BaO, right? So of course the answer is yes. everything will react. Because carbonate react acid, magnesium oxide and barium oxide both are bases, right? So they will react acid. That's why the question writes completely dissolve. Yeah, because I need to convert them to the free cations. That's the purpose. Yeah. Okay. Then the second paragraph reads, the resultant solution was made up to 250, and then I pipette 25 out, and then I get 0.283 grams of barium sulfate. Okay, now you have to ask yourself one important question. Why are they giving you this information? Now, they give you this information simply because, right, from this information, you can calculate the amount of barium present in Somaba. Correct? That's all. That's why most of the time you should be able to, based on this information, tell me the amount of barium 2 plus present in 25 cubic centimeters, and then the amount that is present in 250, and then from here you should be able to tell me what is the amount of barium carbonate present. Yeah, so that is the link. Okay, and then the next thing is, you might be wondering, right? Do I know the amount of magnesium present? Okay, actually, you can tell that easily. To be honest, why is it? I mean, easily, because the first thing is, you are aware between five, between here, right, to here. Oh, sorry, the arrow doesn't go quite nicely. Okay, like that. Okay, the amount of CO2, okay, that gets diffused away, or that gets emitted, right, comes from two sources. It comes from magnesium carbonate and barium carbonate. Okay, it comes from these two sources. Yeah. So if I can determine the total amount of CO2 that gets evolved, technically it gives me the total amount of magnesium carbonate and barium carbonate present. And because I already know the amount of barium carbonate present, right? If I subtract the difference, I will be able to find out the amount of magnesium present. Yeah. So that is why this particular data is important. Yeah. And from here, I will be able to find out what's the number of moles of CO2 evolved. Okay. You can easily calculate that by taking 1.45 divided by 44.0. Yeah. How do you get 1.45? It's 5 minus 3.55. Yeah. So from here, you can easily do that, and that's what the students did. And then after that, you can get the amount of CO2. Okay. And then of course it's being done in a slightly different manner, but at the end of the day, as I said, if I simply take this value and I subtract it from the amount of barium 2 present, which is 0.01213. Okay, so if I subtract 0.01213, I will be able to get the amount of magnesium present. Okay, which is 0.02082. Okay, if I do that, and then because I know the amount of magnesium present, I know the amount of barium present, I can find out the amount of the mass, and of course the amount of sodium carbonate present as well. And then finally, I will be able to determine the percentage of sodium carbonate present. So for those of you who done it correctly, you should get about 17%. Okay, can? Yeah. So make sure you know how to use the data. I know it's a relatively interesting question, but yeah. Okay. For B1, B1 standard question, expect such standard. Remember I said you need to know about the 14 to 18 definitions in your enthalpy changes. Make sure you know them before your blocks. Okay, define enthalpy change of neutralization. And then for B2, I think B2 no issue. Most of you can, most if not all, can get the correct answer, which is -6. 29.3 kilojoules per mole. Okay, remember the units is per mole, kilojoules per mole. B3 is the one that is most of you find a bit challenging. Okay. I don't know if you realize HF is actually kind of like a weak acid. Okay, so for a weak acid, right, you expect the enthalpy change of neutralization to be less exo, which means maybe about -55. But in this case, right, it is actually way higher, no, way more exothermic, way more exothermic than -57. Then they ask you to suggest a reason for the difference. Actually, the reason, right, is not very, very straightforward, but we just want a view from you. Okay, so the idea is more of you should actually focus on fluoride, because fluoride, right, forms very, very strong ion dipole interaction with water. So the ion dipole interaction that fluoride forms with water, right, actually releases a lot of heat. So because of that, yeah, it kind of drives up the enthalpy change of hydration by quite a bit. Yeah. Okay, Ken. So the main idea here is that the enthalpy change of hydration of fluoride is highly exothermic. Yeah. Of course, okay. Some of you try to explain in terms of charge density. Try not to discuss charge density for anion. Usually anion, we don't talk about charge density because normally charge density is related to polarizing power, which is related to cation. Yeah, so don't talk about charge density for anion. But of course, for such novel question, then I think it's fine. We can accept whatever interesting proposal you have, as long as it makes sense. Okay, we are almost done. So for 3C sketch, okay, electrical conductivity, I think you have to remember that your silicon is a semiconductor. Okay, so being a semiconductor, right, means that it can conduct a bit. So just make sure that it's not zero. Okay, so there are three things you need to explain. First is you need to explain the trend for the metals. So from sodium to magnesium to aluminium, there's an increase in number of moles of electrons being contributed to the C or D localized electrons. So therefore, I will expect electrical conductivity to increase. Silicon being a semiconductor, you know, like its electrical conductivity is definitely much lesser than those of the metals. And then for the rest, I think it's good to recognize them as simple molecular and monoatomic for argon. Yeah. So therefore, they are non-conductors. Yeah. So make sure that they are all zero. Some of you give them some values. Yeah. When you drew the graph, you give them some values. It shouldn't be the case. Okay. And then for the next part, if you have read the papers I gave you, you notice that this was actually taken from there. Okay. Okay, at least for D1, right? Discuss how the entropy will change, right? Okay, so when you hit 1 mole of argon, right? I think the best way to explain it really is to focus on the fact that it is a broadening of the maximum distribution curve. Some of you get around the problem by just saying that, you know, there is a more variety, a greater variety of kinetic energy, etc. I think that's fine. But the key idea is the broadening of the maximum possibility. And this broadening, right, will actually result in more ways for energies, or rather more ways for you to arrange the particles in the increased amount of kinetic energies. Yeah, that's fine. Okay. Yeah, and then part two, not an issue. Most of you can get the correct answer. I think the answer for 1 is 0, and then for this is negative. Yeah, because for the case of 1, the accessible volume is the same as before. For 2, the accessible volume diminished. Okay, yeah. I mean, that's about it. Any questions from the rest? Oops.
Mr. Wee, could you show the calculation part for part
Yeah.
3 again?
Calculation part for question part 3.
part 3. Like 3A part 3.
Oh. Wait. Wait. Okay. First, just give me a while. Okay. The first thing you need to do, right, is to calculate the mass of CO2 loss, which is 1.45 grams. Yeah. Why is it necessary? It is necessary because from here, right, if you convert to number of moles of CO2, right, it tells you the number of moles of barium carbonate and magnesium carbonate present. Yeah, because the CO2 comes from only two sources, magnesium carbonate and barium carbonate. Because you were told that your residue consists of magnesium oxide, barium oxide, and sodium carbonate. So therefore, sodium carbonate not decomposed. So the mass of CO2 loss, this mass, the CO2 must come from the decomposition of magnesium carbonate and barium carbonate. Yeah, so the number of moles of CO2 is the same as the number of moles of barium carbonate and magnesium carbonate from the balance equation you have written for part 2. Of course, assuming that you have written a correct balance equation, which I showed you earlier on. Yeah, then, yeah, so that's the most important data. The next important data you need is actually here. Here. Because you are told that after you have added 25 cubic centimeters of standard solution to sulfuric acid, right? You get 0.283 grams of barium sulfate. So from here, it allows you to calculate the amount of barium sulfate in 25 cubic centimeters. Yeah. So therefore, from here, right, you can perform one calculation. You can perform the number of moles of BA present in BA2 plus 25.0 cubic centimeters. So that is simply 0.283 divided by barium sulfate, which is 233.4. Okay, so this will be 0.001213 moles. Yeah, then after that, you scale it. Scale to 250. Yeah, if you scale to 250, you'll get the amount of BA present in SOMABA, which is 0.01213 moles. Yeah. Then because you already know the total amount of CO2, which equals the total amount of barium carbonate and magnesium carbonate, and you know the amount of barium carbonate, right? You take the difference, you will be able to find out the amount of magnesium. Yeah. Okay. Okay. So then from here you can calculate the amount of magnesium present, which is equals to earlier on is this, right? 1.45, right? So I will simply take 1.45 divide by 44 minus 0.01213, then I will get 0.02082 moles. Yeah. So if I get the amount of magnesium, which is this, and I get the amount of barium, which is this, I can calculate the mass of barium carbonate, right? And I can calculate the mass of magnesium carbonate. Then I know the total mass, which is 5. I take the difference, I can calculate the mass of sodium carbonate. Yeah. And then from there, I can calculate the percentage mass. Yeah, that's it.
Thank you.
Hi, Mr. Wee. Sorry, just now I think you were not very clear because of Wi-Fi issues at 3 part D. So could I ask you to help to explain the Maxwell-Boltzmann distribution curve part again?
Oh, okay. D1 is it?
Yeah, D1.
Okay. Okay. Okay, so for D1, right, basically, when you plot your Maxwell-Boltzmann distribution curve, proportion of particles against KE, for a normal temperature, let's say, in this case, let me just share my screen first. Sorry. Yeah. Okay, so let's say you have a proportion of particles. Let's say this is 298 Kelvin. And then for the other case, I heat up to, what's the temperature? 398 Kelvin. You realize that your Maxwell-Boltzmann distribution curve actually broadens. Yeah, so the broadening of the curve, right, it is an indication of the fact that now a greater proportion of particles is able to access higher KEs. Yeah, so because it's able to access the higher KEs, right, that actually means that for the same number of particles, right, there are more ways to distribute it amongst the wider range of KEs. So this actually leads to a positive entropy change. Yeah. Yeah, that's about it.
Thank you.
Okay. Is that fine? Anyone else with any queries?
Mr. Wee.
Maybe
for question 3, part B, part 3, right? For the hydrofluoric one, like the answer was that the enthalpy change of hydration of F minus is highly exothermic, right?
Yeah.
I wrote that hydrofluoric acid, it ionizes more readily.
Yeah, but actually it doesn't.
Oh.
It doesn't. It's actually it's a weak acid.
Oh.
Yeah. So cannot argue based on the fact that okay, so it's like so for hydrofluoric acid is an interesting acid lah, because it's a weak acid, and yet the enthalpic change of neutralization is highly exothermic. So it's like one in 1 million kind, or 1 in 1 trillion, maybe not even 1 million. Yeah, like it's quite rare to get this kind of situation. Yeah, so whenever you so in that case, HF, right, hydrofluoric acid, actually it's an interesting acid that people actually done a lot of research for 50 to 100 years, for the past 50 to 100 years. They actually found a lot of information which I don't think I want to share with you here. Yeah, but of course the main thing is it has got to do with the fact that fluoride is the unique one that actually contributed to the highly exothermic nature of the reaction. But of course, you can't exactly prove it by just me talking lah. I mean, I'm sure if I talk about it, then you will think, how do you know lah? They have done experiments, of course. Yeah, but if you look at the nature of the question, it's actually a suggest question. The question is just asking you to comment and suggest. So actually, any answer that makes sense will be fine lah. You know, yeah. However, okay, I need to caution you also lah. However, the answer cannot be assuming that HF is a strong acid. You get my point? Because if HF is a strong acid, right, then there isn't a need to even hydrate. You agree? Because I don't need to hydrate, it's already a strong acid, right? So HF will be what? H plus and F minus. So the F minus is already hydrated. So it won't give out energy, it won't give out heat anyway. Yeah. So it has to be based on the fact that, my HF is not hydrated at the start. Okay, my HF is of course hydrated. It's solvated, dissolved, right? But in the course of the reaction, right, I form F minus. And then F minus gets hydrated, which releases the amount of heat. So that's a different ballgame, because the amount of heat is more than the amount that is being generated by the neutralization of H plus and F minus. H plus and OH minus, because it's an acid-base reaction. It's more than that. Okay, and it's even more than enough to compensate for the dissociation of HF. Yeah. Remember the usual argument we have, why is the enthalpy change of neutralization between weak acid and strong base less exo? The usual explanation we said is because the heat generated from the acid, from the reaction between H plus and OH minus, right, is being used to further ionize the weak acid. So therefore, one is exo, one is endo. So it compensates a bit. So there's some amount being taken away. So therefore, it's less exo. But in this case, right, yes, some of the heat is used to compensate for the ionization of HF. However, right, the solvation for fluoride is so exo that it created even more heat, extra heat. So therefore, what you get is actually a huge number. In that case, negative 69.3.
Okay, thank you.
Yeah, okay. Anyone else? Okay. If not, then I will bid farewell to all of you. Okay, then I will see you when school reopens. Bye-bye.